Okay, I think it's time to start. So welcome back. Now we have our first invited talk of the working group workshop. So we have Dima from Cambridge talking about functorial models of scope-safe syntax.
Lovely. Thank you very much. Thank you for the invitation as well, Andreas and Marie. It's a great honor. I'm always a bit anxious about talking about my work because I feel like I need to justify why is it interesting to study syntax and substitution and variables, even though they sound... Sorry? Closer. 1, 2, 3? Good, okay. Yeah, why is it interesting to study substitution and variable binding, even though they look quite trivial? Then I looked on the website for the meeting and I saw that the feature appears quite in a lot of talks, so I think I'm in safe hands, and you will understand the struggles of the work. So I'm not going to talk too much about why syntax formalization is difficult. We have all these kind of issues with encoding of variables and representation of binding. Because it's a challenging problem, there are also loads of different solutions and proposals for overcoming the difficulties. Some of them are slightly more like implementation specific. So for example, De Bruijn indices, which are used to represent variables in many compilers, are a good way to do this, although they're also quite messy to work with and difficult to reason about. Lots of the techniques are more formalization specific, for example. So if I want to reason about the meta theory of the language, I'd like ideally some sort of representation of binding of variables where I don't need to worry too much about like types or terms which are not well scoped, not well typed. So I can focus my theory on well typed terms, for example. So a central notion really to the study of syntax is the semantics, because we think of syntax as the initial semantics. That is a semantics which doesn't have anything extra in it, so that I can interpret the syntax into any other model of the syntax. And lots of the components which will feature in this talk are going to be about axiomatization of the syntactic structure. So in some ways this will be encoding all of the constructors of the syntax, but also, more importantly, which isn't really featured in like second order languages, is the axiomatization of substitution as well. So models will also have to account for what does it mean to represent variables, what does it mean to encode and perform the substitution of terms into variables. And the syntax, of course, has to account for this as well. The main tool for lots of these semantic investigations is going to be the initial algebra semantics, or the initiality proof of the syntax. So we need to show that out of all the possible models, so objects, mathematical objects, which have the syntactic structure and also have notions of variables and substitution, we want to show that the syntax is the initial such thing, so that given any other model, I can interpret the syntax in the model in a way that preserves the constructors, but also preserves the substitution and the variables as well. And this will give me lots of useful correctness properties that I can rely on in my work. In practice, often we use the semantics as the sort of direct interpretation in some sort of denotational semantics, for example. But also, it gives us recursion and induction principles. So sometimes the initiality will be used not in a semantic model in a sense, but some sort of object derived from the syntax itself. So I can derive syntactic operations as a semantic interpretation. And we'll see examples of this in a bit. So as a probably very familiar example of what initial algebra semantics is, the syntax of natural numbers, which just consists of the zero constructor and the successor constructor. So when I think of syntax, I just think of the data type declaration in some sort of functional language like Haskell or Agda or Coq. And it's, as is well known, a model of these piano natural numbers will be a set with a single distinguished element and also a endo function, and these will correspond to the two constructors. One will be the zero element and the other one will be the successor element. And the initiality means I have this recursive definition of the denotation of natural numbers in any model of natural numbers. So the zero constructor is mapped to the zero element, and the successor is mapped to the successor function when I recursively interpret the natural number there. So the recursion principle there comes from the initiality of the model, of the syntax. So some examples, of course, I can interpret the set of natural numbers, the syntax of natural numbers in the set of natural numbers by interpreting 0 as the number 0 and successor as the +1 operation. I can also do some more interesting things, like interpret them in sets where the 0 will be the unit set and the successor will be the maybe monad, so essentially the +1 constructor. But then these examples are when I use semantics to define syntactic operations. So for example, the addition operation on the natural numbers as a piece of syntax will be the interpretation in the function space from naturals to naturals, where the 0 element will be the identity function, so it returns the other argument of the plus operation. That will be the 0 case for the plus, and the successor composition will be the successor case. So when I put everything together, the interpretation of successor m times and 0 will be a function from successor n times into a successor m plus n times. Also, you can interpret it in other syntaxes, like Boolean natural numbers, Booleans, and these could correspond to predicates about natural numbers, like evenness. So another example, at least it starts with as an example, is the syntax of the lambda calculus. And when I thought about what is a model of a lambda calculus, I always think of, well, it's the interpret types as sets and interpret terms as functions between contexts and types. But actually, this is a particular model of the lambda calculus. There are many other models. This is the one that we study in sort of the initial semantics land, but it doesn't give me the ingredients and requirements that I want from a semantic model, where I can generalize and generically talk about interpretations, derive syntactic operations using initiality. So this talk will be about a few of these possible models which have been introduced and developed over the last 20, 30 years, which proved to be powerful enough to encompass a lot of interesting properties of syntax. And the nice thing about them is they can be generalized to generic syntaxes. So if I fix the notion of I'm only going to think about simply typed languages, there is a class of models which encompasses every simply typed language, which in practice means if I develop a framework to formalize the generic meta theory of languages, I can have a library, for example, which, given some sort of syntax description, derives for free the meta theory of the language in some sort of proof assistant. And that's what I've been working on the last couple of years. So what exactly is going to be a model of syntax? So first approximation will be via the signature endofunctor. So endofunctors are very often used to encode syntax because they correspond to, or kind of combine together, all of the constructors of a syntax. So, for example, natural numbers, they have two constructors, and I'm going to construct the endofunctor corresponding to the signature just by looking at the domains of the constructors, taking their coproduct, because functions out of a coproduct will be a tuple of the functions. And then I'm going to say that this +1 will be the natural number and signature endofunctor, such that algebras for this endofunctor, so functions from fn at n to n, will be exactly the models of natural numbers, because they come with these two constructors, one corresponding to the 0 case, the other one corresponding to the successor case. Other similar example, binary trees. I have two constructors again. Now these are parameterized by a set of types in the tree, and again, the tree, the syntax itself will be the initial such endofunctor, but in general, a model will be an endofunctor. An initial algebra for the endofunctor, but in general, any other algebra will have the structure of the constructors of these data types. So this is a very well-known formalization of data types or of algebraic data types as initial algebras. The question is, does this extend to endofunctors other than set to the set? Because set to the set is the essentially the types of normal algebraic data types which we have in functional languages, but it doesn't encompass richer syntaxes which also try to account for variable binding contexts and so on. So the first approach that I'm going to talk about is the monadic approach. I'm going to talk less about this because I'm not exactly an expert in this one, and there are people in the audience who invented it or researched it quite a lot more heavily than I have. But hopefully I will show some of the commonalities between the monadic approach and what I'll later talk about is the pre-sheaf approach. So the first idea the first work which proposed that syntax should really be a endofunctor, or at least even a monad, was by Bellegarde and Hook. Weirdly enough, they didn't actually invent what we now know as intrinsic syntax, where I keep the context and sort of index the context in the type language itself. They used this as a sort of convenient way to formalize normal De Bruijn index formalization of syntax. And it took a couple of years, 5 years, to actually connect this to nested data types and the ability to say that in the lambda constructor, I'm going to actually extend the set of variables or the context that I keep track of to encode that the lambda constructor binds a new variable in its body. So here, this x parameter corresponds essentially to the kind of world of variables or the contexts. And I can, using nested data types, I can encode these kind of binary relationships and say that some subterm of a constructor actually binds some new variables. And then Artenkin and Royce, they formalize this to say that syntax, in this sense, is the initial algebra in this category of endofunctors. And in fact, it has monad structure, which comes from the initiality of the syntax itself, which corresponds nicely to the idea that once I have defined the syntax for some sort of, defined the data type for some sort of syntax, then substitution and renaming and all of these meta-theoretic operations, I do that by recursion in the syntax. So it's a syntactic operation. I should be able to derive it from the fact that it is the initial algebra. And it's not something I should really need to do by hand, per se. So the fact that we have this type-level access to X, which is in this interpretation going to be a set of contexts, means I can control what kind of terms I'm talking about. So for example, if I say I have an element of term in the empty set, that means it has no variables that I can use. So it must be a closed term, so no free variables rather. I can of course bind new variables, and then the binder term will have an extra variable that I can work with. But it means that I can't just invent new variables. So the nice thing is all of the issues that we had with De Bruijn, numeric De Bruijn indices, where it's very easy to go out of scope with the numeric De Bruijn indices, are avoided because I can just explicitly say the term has no free variables. Operations such as term x to term 1 plus x corresponds to the standard structural properties like weakening, for example. So if I say I have a well-type term, I also have a well-type term in the extended context. In constructive settings, this becomes an actual function that I need to write. So if I do this as a pen and paper proof, and I don't need to really convince the computer that this is all correct, it's quite easy to hand-wave things like weakening and say, okay, it's obvious because, of course, I'm not using any of the added variables in the original term. When I'm working in a proof assistant, then I need to make this into an actual construction because I need to shift around the essentially De Bruijn type-level De Bruijn indices to make sure everything lines up correctly. So some examples of the kind of terms that you can write in this work is I can have a closed term, and I know it's closed because it's typed in the empty context. Essentially, this is just the function application function. So it takes 2 arguments, and because I don't have access to named variables, I need to play with these De Bruijn indices and encode them, but now there are the numerals, they will be encoded and constructed in type level. And because the +1 constructor is just the maybe monad, I can use some and none to refer to the first or the successor indices numeric de Bruijn indices. So a subterm of this term, after I've bound two new variables, will be a term in the twice extended context, so I can refer to the first variable as var none and the second variable as var sum of none. So you can think of none as the zero and sum as the successor, just as we had before in the initial algebra for natural numbers. Because this model of endofunctors, where the syntax is just a functor from set to set, it does mean that I can put anything as the set of variables. So there's nothing stopping me from making terms over lists of terms of complex numbers, and it's not really obvious what this means. It really only works when I start from a closed term for the empty set, and I use this essentially successor operation, extension operation, to add the new variables, rather than having an arbitrary family of terms. And the pre-sheaf model will make this very concrete because it will only limit us to functors over contexts rather than arbitrary sets. So the big realization here that the term endofunctor here is a monad, and the monadic structure corresponds exactly to substitution. So the variable embedding, which is goes from the variable set of variables to the terms over the variables, is going to be the unit of the monad, and this multiplication operation, which means collapse all the nested terms where I have a variable applied to a term itself, is going to be the join operation. It's not nearly as simple as just saying I'm going to remove all the variable constructors, because you need to do a lot of the shifting of indices around, and that leads to a lot of complexity actually, but that's the intuition. You just remove the var constructor from the term itself. The other presentation of substitution here, of course, is the Kleisel extension. So what I would more generally think of substitution is I have a mapping from variables to terms in another context, and I end up with a function from terms in the first context to terms in the second context. And of course, these are join and sub are interrelateable. I can't, as I said, I can't define these as directly as this. I need to actually manipulate the context and shift things around, and that leads to a lot of this boilerplate code that I need to write whenever I try to formalize some sort of syntax. But it's generally quite, once you understand what needs to be done, which is basically write all the definitions and improve all the lemmas you might think you need, because you probably will need them at some point. It's a very systematic process, which means, of course, it's quite easy to automate as well. So these definitions, they depend on two very important operations. One is map, or functoriality, essentially. So this is what it means for syntax to be an endofunctor. I can rename the contexts of variables with the map operation. And then lifting means if I have one of these functions from x to tmy, which you can think of as substitution of variables in x to terms in y, I can lift it or extend both contexts by an extra variable to have a substitution which maps now an extended context. Sorry. I probably did, yeah. Yeah, I did. Thank you. Yeah, you can do that by a swap at the end. Yeah, sorry about that. Yeah, so you get a term in the extended context rather than an extended term. You can define lift using this more primitive operation of swapping. It's basically, if you think about it as a distributive law between two monads, and it means if I have either nothing or a term, I can return a term in an extended context. And indeed, you would take this and then post-compose it with swap, and that's how you get the actual lift that you need. Yeah, so as a flavor of the kind of definitions that you end up writing, you want to end up with the join here. You can't really define join directly, at least I tried long and hard, I didn't manage, maybe you can. But it is possible to derive it from substitution, which is the Kleisel extension, but you can only define substitution if you know how to push substitutions, which are these f's, into under binders. So whenever you have subterms which do not have new binders, it's just normal recursive application. But when you have a new extended variable, you need to extend the substitution itself, and that's exactly what lift does. And as I said, lift is map f with a swap applied to it. And swap is defined by case analysis, where I need to, in the sum case, I need to weaken the term by a new variable. So if I have a tmx, I need to end up with a tm1 plus x, which is why we need weakening. But weakening is an instance of renaming, when I just say I'm going to extend x with one extra variable, and I can define it using map. And if you think you can get away with just defining weakening once, no, you need the whole map, unfortunately. And then map is actually definable because this is going to be the essentially lifting for the maybe constructor, and the map for the maybe constructor. If you want to prove properties about this, so the monad laws specifically, about the unit of substitution and associativity, there is a whole host of properties to prove. And you need to do them essentially in order, but of course you start here and then you figure out what you need to prove by trying to prove it, and then getting stuck inevitably. And then you get stuck and you start proving something slightly more specific than you need, for example, some interaction law between lift and weaken, and then you realize, no, you need all of map. I hear some laughs in the audience. This is a pretty frustrating process if you don't know what you're doing. And yeah, I'm not going to talk about the torture of this, but you need to do this kind of stuff. So the nice thing is all of these properties, once you have proved them, they do generalize lots of the familiar properties of substitution that you might need in any kind of more interesting meta theory once you actually move on from defining syntax. So the unit substitution, so if you this actual substitution step, that should be an X, is going to be one of the unit laws of the monad. The other one will say that if you have a term which has no occurrences of X, then substitution will do nothing. And the third one, for the single variable case, will say you can reassociate things in an expected way. So what are the models of this approach as before? So we said models are built on endofunctors in set, and the signatures are going to be endofunctors on the endofunctors themselves. So I can define, for example, the lambda calculus as the two constructors going from the extended context of Tm and then two terms into a new term, combine them into a single algebra constructor, which goes from sigma L applied to Tm applied to X. And this expands into this definition of sigma as mapping an endofunctor and a set into this sum there. So an algebraic model is just going to be an algebra for the endofunctor constructed from sigma and the identity, which is going to correspond to variables. And then syntax is the initial model, which we know is going to correspond to an isomorphism of algebras. So you might ask now, what is the relationship between this algebra structure and the monad structure that we have? Is it the case that the algebra is somehow preserving the monad structure? Is it that the monad structure preserves the algebra structure? Unfortunately, neither of these is the case. And this was discovered and fixed by Hershowitz and Jesse in their work on modules over monads. And this has been developed quite a lot further by many other people since. So rather than talking about monads directly, we now talk about modules over monads, which are sort of like one-sided monads in a sense. So a module over a monad will be a functor which one precomposes with a monad, you can remove the monad application from the beginning, and it satisfies the associativity laws. A homomorphism of these modules is going to be called the linear map, and it's essentially, again, just like a monad homomorphism, except you don't touch one side of the monad multiplication. So it's a generalization of the monad multiplication operation. And then you can define a signature which respects substitution structure as a mapping from monads into modules for a specific monad. And I'll show examples in a sec of what that means. So, for example, if I have the delta, which I'm going to be using for the context extension endofunctor, which applied to an endofunctor just extends the context of the endofunctor. If you have a module S over T, then you can also turn delta S into module by applying swap, which will swap the extension and the monad around, and then inside the extension you apply the module structure for alpha, and you get delta S A. So that means delta S composed with T is can be mapped to delta S, which means delta S is a module for T, or over T rather. And delta is of course one of the components of the syntaxes for the lambda constructor. So in general, if I have some sort of signature for a syntax, I can turn it into a signature in this sense by saying that if I have the which way things go. So going down is going to be the monad operations. So this says that going down going to be in the module operations, and every monad is a module over itself. So mu is the module of T over T, and then this composition will be the module of delta T over T. And I can say that L, which is the lambda constructor, will be a linear map between these two modules. So if you do the lambda applied to, if you do the mu monad multiplication at a lambda, it can be derived as the lambda of the extended substitution operation. So these laws essentially axiomatize what you would do when you want to define substitution in the end-effector model. So one important component of this is called the strength operation, which, as we can see here, is what we applied here to push the composition of delta with T under the delta, and then composition of T inside the product here. And these are the so-called strength transformations, which essentially just means if I have an endofunctor sigma applied, endofunctor applied to A, I can push a precomposition under that sigma, and it satisfies some axioms as well. And whenever I have this transformation, then I can always turn, if I have then I can turn this into a signature in the sense of it being a module over T, because I can just push composition with T under sigma and then apply multiplication between them. And that's how you can generate modules over T from an endofunctor, given that it's strong in this sense. Then we can prove initiality results. So I'm not going to go into the details too much, but with enough properties and enough axioms on sigma, you can show that the initial such model, Tm, is indeed going to be, the syntax is indeed going to be the initial model, because given any other model, I can define this unique monad morphism from terms to this new model, which is a monad morphism, so it preserves substitution, but also it's a module morphism, which means it preserves the algebra structure. This means it sort of automatically satisfies the semantic substitution lemma, which is interpretation of a substitution will be the composition of the interpretations. So a couple of pros and cons of this approach. It, of course, has seen a lot of work, especially the modules over monads approach. There's work ongoing on syntactic translations and also operational semantics, because the presentation of models via this module over monad way admits the notion of operational semantics a lot better. But as we mentioned, having endofunctors everywhere means there's a bit more generality in the category of context than we need. And also, just because we have sets everywhere and sets over sets and sets over sets over sets over sets, there's a lot of sort of homogeneity in the model, which can make the theory quite confusing. So even things like what's application versus what's composition, just notationally can be a bit tricky, because when I say Tx, I need to know whether T is when I say TT, for example, I need to know whether it's a composition or some sort of application form. And all of these mean different things, but it's not a priori obvious what's going between what categories. So there's a loose hierarchy between the different levels of the work, because it's all just sets or endofunctors and sets. I don't have something specifically to say this is a term versus this is a type, this versus this is a context. So this is what the pre-sheaf approach is trying to resolve. is have an actual hierarchy between what is a context, which is the thing that I'm indexing variables by, versus what's the category of terms. So this is the work initiated by Fiore et al. And they said, well, syntax lives in presheaves, which are essentially categories of sets indexed by contexts, which also admit some sort of renaming operation as part of the structure. And extended to a sorted setting, which is when I actually have types in the language, you can just talk about sets being presheaves indexed by another set of terms. So for example, the set of terms for the lambda calculus or any kind of syntax will be a family of sets which varies over the category of contexts and renamings. And it also comes with a variable renaming operation which maps gamma to delta, which is going to be a renaming from context gamma to context delta into a function of terms from terms in gamma to terms in delta. So some commonalities between the two models. Again, renaming here is baked in the definition, so I can't get around working in a meta theory where I don't define renaming, which means when I need it, for example, for weakening and lifting and so on, it's already there, which is quite nice. However, contexts now are a distinct lower class object, which have often some sort of specific syntactic structure as lists of types, for example. So there's no arbitrary function space. I can't apply syntax to an arbitrary set. It always has to be a specific context. It also means, of course, the monadic model will not apply here because I can't compose monads. Sorry, you can't compose, no, you can't compose monads in monads. You can't compose presheaves because they are not endofunctors. But you do have a result that presheaves over F, which is the freely generated free co-Cartesian category over a set, but think of it as just contexts, is equivalent to the category of endofunctors as long as the endofunctors are finite trees, so they represent finite operations. Yeah. So presheaves, because they are now specifically indexed by contexts and types, they have this structure which we sort of refer to in formalization as intrinsic typing. So terms in a presheave are, by their nature, they are indexed and well-typed and well-scoped in a specific given context. There's a distinguished presheave of variables, which is, you can think of, well, it's defined as just the set of renamings from the singleton context to gamma, but you can think of it as a proof that alpha appears in gamma. And actually the category of contexts has the coproduct structure where you have you can think of it as a constructor of new, which points to the top variable of a context, and old, which maps to or points to the rest of the context. So it's like the head and the tail of a context. They come from the free co-Cartesian structure. What's quite nice is that context extension, which is this delta operation, it can be defined in terms of presheaf exponentiation by variables. And presheaf exponentiation is a weird operation, but you can show this by various magical Unida means that this holds. And what it means is that the evaluation, once I translate p to the v to delta p, which is context extension, it corresponds to the strengthening law. So when I say p is well-typed in the extended context, but then I have a proof that the tau variable appears in gamma, then I also have that the term is well-typed in the non-extended context. So signatures in the presheaf model, they are still endofunctors, but now they are presheaf endofunctors. So because we now have sorting and typing, the definition itself gets a bit complicated, but it basically just says, because I need to index the output by a tau, which is the output type of the constructor, all the terms are again just going to be the different constructors. So this one, for example, corresponds to application. So there must be a input type for the function such that I have two terms, one going from the input type to tau, and then p to tau. So if I go from here to here, that will exactly correspond to the type of application. In here, I need to make sure that tau actually has a function structure when it's a binding operation. But if you work in an untyped setting, this will still look very similar to the previous endofunctor approach. And as before, we have models are going to be algebras for, sorry. So this one is extension, lambda. So it means this is basically have to be an inequality proof that tau is a function type, and then the body of the function will be an extended context. And here, I don't need to specify anything. I can just use tau. It should be, indeed, yes. Yes. Next one. Yes. Okay. Small typos. Apologies. Hopefully, it's just these lower index things which are wrong, not the big letters. Right. So, in the endofunctor model, substitution structure is relatively straightforward because it is endofunctors and monoids within endofunctors are monads. So it's a very nice familiar structure. We can't really do that, of course, here because presheaves are not endofunctors. So we have two choices to get around the issue. One is the introduction of relative monads, which are come from a paper aptly titled "Monads Need Not Be Endofunctors." And a quick definition here. So a relative monad along a functor J is going to be a functor F, which comes with essentially a monad and a unit unbind structure, except I have a J here to turn the codomain of things into the right category. So the unit here is from JA to FA, and this extension or bind operation goes, with a normal monad, it would go from A to FB. Here it goes from JA to FB. And this is indeed the structure that we have with presheaves as well, except these are going to be V relative monads. So variables will go from variables alpha gamma to terms P alpha gamma. And the extension will go from variables alpha gamma to P alpha delta, which is the substitution rule. So it's a mapping of variables of to terms to a mapping from terms in gamma to terms in delta. And you can indeed axiomatize syntax in this sense as well. But there's another way, which is what I'm working with, and that's to axiomatize this as a monoid and a special kind of monoidal category. So a monoidal category, you probably are familiar with, it's a category with a unit object and a tensor multiplication with these isomorphisms corresponding to the two unit operations and associativity. And in our specific case, we have the monoidal structure of presheaves given by this kind of ugly looking thing, and I will decompose what it means really. So first of all, this operation gamma q delta is one of these substitution rules that we have. So for every type, if we have a variable of that type in gamma, we map it to a variable of the same type in delta. So it's going to be like a simultaneous substitution rule on the syntax. And what this coend thing is doing is elements of this will be dependent tuples, so will correspond to a context, a term in that context, and a substitution from that context into delta, which is the output context. And the coend, which is a special kind of colimit, it performs a sort of quotienting or equivalence conditioning on the tuples. So it enforces some sort of internal renaming invariance. So if I have a term which I associate with a substitution which I sort of pre-rename, I can also rename the term first and then perform the substitution as normal. And this is a quotienting because these are tuples equated by this condition of the coend. And this is essential for proving the invertibility of the structure maps, and lots of the various properties of the presheaf model depend intimately on this coend condition being there. And then within this monoidal category, a monoid object will be an object with a unit and a monoid multiplication like this. So in our specific presheaf model, one of these monoids will come with a family of operations, which if we decompose this for every gamma and delta and every time alpha, if we have a term in gamma and a substitution from gamma to delta, we get a term from in that should be a delta. Oops, okay, sorry about that. We get a term in delta, and that's exactly the type of a substitution operation that we expect. We have a substitution from gamma to delta, and we turn it into a substitution of terms into terms. And the naturality of this pre-sheaf transformation and the dinaturality of the transformation, which corresponds to this quotient condition, means that the substitution has these renaming axioms, essentially. And if you squint and turn it into Agda code, these might be familiar ren and sub interaction properties that you've seen. So if you do a substitution first and then do a renaming, that's the same thing as doing a substitution with a renamed substitution rule. And if you do a substitution with a composed substitution, you can turn it into a substitution with a renamed term. So models in this setting now are going to be monoids which come with the substitution structure of the monoid, but also an algebra structure for a specific endofunctor. And I want these to be compatible. So just like with the modules over monads approach, I want to say that the substitution and the algebra structure sort of interact in a nice way, and that's what the notion of a sigma monoid is about. So it's a monoid with an algebra structure such that this diagram can meet. So again, if you think of this as the defining property of the recursive definition of substitution, to define substitution on any kind of constructor, I essentially just apply the substitution on the subterms, on the sigma, perform the constructor structure, and then this lowercase sigma is the so-called pointed strength, which we've seen already in the endofunctor sense, which is responsible for pushing the substitutions into the subterms of the constructor, and specifically also under the binding terms as well. And as before, we can prove initiality formally, or if you want to do this in a proof assistant, you need to go through this several-step process of, first of all, you define your syntax TM, you define the renaming operation, you define this strength operation, which is done, well, for most cases, it's going to be quite simple. If there's binding involved, you need to apply this lifting transformation as well. Then you derive the substitution operation either by hand or by initiality. Then you need to prove a bunch of these laws that we've seen already in the endofunctor sense. And then given any sigma monoid M, you can define the initial interpretation from the term pre-sheaf into this monoid, and then prove that this preserves the sigma monoid structure. So, what are some pros and cons of this setting? It's also been studied quite widely and extended to lots of mathematical settings. And in my opinion, at least, the fact that we have this category of contexts and pre-sheaves and double contexts, and pre-sheaves are objects rather than, like, they are things rather than transformations from sets to sets in a sense. In my head, that's easier to keep track of and have in my mind. And yeah, it does not really lend itself very easily, though, to things like operational semantics. So you can do very nice equational theory and second order abstract syntax features with this, but it doesn't obviously lend itself to operational semantics, and that's going to be future work. It is also quite mathematically involved because you're dealing with lots of categorical structures like coends and pre-sheaves and so on. It's not as direct as just a type constructor in a templating type setting. So the family approach, which I'm not going to have too much time for, but I'll run through some ideas, is what I've been working on, which is take Marcelo Fiore's work on the family or the pre-sheaf approach and make it actually adaptable to a dependently type setting, which doesn't have lots of the mathematical features that it really relies on, like quotienting, for example. So the pre-sheaf model, because it is not intended to be there for formalization, is quite computationally expensive. If you try to formalize it with a category theory library in Agda, for example, the Agda type checker will sort of die quite early on because there's a lot of like functors and natural transformations and lots of laws to prove and check as well, and it just becomes very difficult to handle. So directly, it's not easily interpretable, and the fact that we don't really have access to quotienting without using quotient deductive types, which is another level of complexity, makes it difficult to work with in practice. But in fact, we know that we can work with this in practice if we don't use a pre-sheaf model. We just do it by hand. We just need to do some workarounds. And what's also interesting is, if you look at the model, the only place you really need renaming is the strength substitution, so the weakening of terms when you do capture avoiding substitution. That's the only place you really need weakening for the whole system. And in fact, in the original pre-sheaf model, when you go into meta substitution, meta variables, there are things where renaming is actually quite harmful, and you don't want to do renaming there, but you need to push that formalism into the pre-sheaf model by turning the families, which shouldn't be renamed, into pre-sheaves, which can be renamed, but without actually changing the underlying family. So there are lots of elements of the pre-sheaf model which actually quite lend themselves quite nicely to a formalization without using pre-sheaves at all. So our work, which has been presented at POPL in 2022, we claim that actually a lot of the work can be adapted to indexed families without any a priori pre-sheaf structure. And this puts intrinsic encoding in languages like Agda and a nice, elegant formal foundation. So we work around the need for quotienting just by saying that most often than not, you can get away without quotienting just by focusing on dinaturality. And we still get a lot of the properties of syntax, individuality properties of syntax, which can be provably pushed into the pre-sheaf model and say that if you have some sort of property of the family model, you can find a corresponding property in the pre-sheaf model as well. I might just focus on which bit? Yeah, so a couple of challenges. First of all, of course, because we say we have indexed families, we don't have pre-sheaf structure, but we can request this structure, renaming structure explicitly just by saying, I have a family which has a renaming operation, which I encode as this algebra structure for the diamond operation, which groups together a family with a renaming operation. Once you work with these categories of algebras for this essentially free pre-sheaf monad, you lose a lot of the nice properties of families, but also pre-sheaves. So, for example, families are not a priori monoidal because I don't have the renaming structure. But when I work with these diamond algebras, they don't have this weaker structure of skew-monoidality either. So skew-monoidality just means my structure maps are not invertible. So a lot of work is going on at the moment in trying to make sense of this and figure out how exactly is the pre-sheaf model different from the family model in this sense. And especially focusing on strength, which as formulated in the original pre-sheaf model doesn't work in our setting because the category that we are pushing into the constructor is not monoidal at all. A lot of the axioms that are needed, which generalize these lifting lemmas that we see in formalization, they need to be adapted into the family setting. And I'm running through a lot of this at a very high level, but details could be found in the paper. Yeah, and as I said, you can show the same kind of inertiality results here as well. So to summarize, the family model embeds the pre-sheaf model into a dependency type setting. You lose some of the nice features, but you can, in a mathematically motivated way, hack them back into the system. And it makes it amenable to practical formalization. In fact, you can start with the syntactic description file, and then I have a Python script which turns that into a quite robust tagged formalization for the syntax. And yeah, I'll stop here. Thank you.
Right, thank you for a nice talk. Are there comments or questions?
Torsten? Oh, sorry.
More of a question, maybe you're aware of nominal sets.
I'm aware of nominal sets.
Right. I mean, in the end, nominal sets are just equivalent to a pre-sheaf category, but it uses a different vocabulary.
Yeah,
so I was wondering if this might be more amenable to formalization. And also as a follow-up question, because you were at some point basically showing by hand that terms form an initial algebra. But in the end, what you can then do is you have certain building blocks, if you wish, of functors that you can put together, and you know they will have an initial algebra given because they preserve certain co-limits. So that would make that part easier, right? You know that you will get an initial algebra. So I was wondering if you had given any thought of using this particular terminology over general pre-sheafs.
Right. So first question, there is a lot of other ways of doing variables and binding and names and so on. Nominal sets are another very mature model, which actually focuses on, let's not use de Broglie indices at all. Let's actually name variables by names. It's quite difficult to put into a dependent type setting, and that's what I'm focusing on, because it's not obviously a constructive model. You still have notions of quotienting there. About the other question, I'm kind of living in two worlds. I'm living in the world of category theory, but also living in the world of practical formalization. And a lot of the kind of things that you do in practical formalization, which is just, I want to define the data type of terms, and I want to have a substitution operation on it. It's a lot less practical to derive the family of terms, for example, by some other abstract means, especially if it involves co-limits and quotienting and equalizers and so on. So what my goal is to start with this syntax description file and extract a AGDA file which has the actual definition of the term and via minimal means derives all you need to know about the syntax and the meta theory from that directly, rather than trying to do it in some sort of encoded way when you combine functors together and compose these initiality proofs. But I can appreciate that, of course, that is more efficient to do on paper, perhaps, but not always in computer.
Okay, let's take the time for one more quick question.
So thank you for your talk. So I have a small question because I see what you're trying to do, especially with the endofunctor sigma, which is some kind of signature. But I liked your story about monads and lambda calculus at the beginning, and for me it's very convincing. And in this whole Fiore line of work about abstract syntax, I was wondering if there was, there is a monad of clones on your category F, and I was wondering if you could see this endofunctor sigma as some kind of object of the endofunctor category, and then have monad on that category. I don't know if it's clear or not, but so the idea would be to you take a endofunctor signature, and you see this as an object on which you will apply a monad, and this will give you like the free object.
So when you say endofunctor signature, do you mean in the endofunctor model or the pre-sheaf model? A signature endofunctor on endofunctors or pre-sheaves?
I think it will be pre-sheaves, but
pre-sheaves.
Yeah.
Okay, so you start with the endofunctor on pre-sheaves, and then what's the next part?
I mean, okay, perhaps we can talk about.
We can discuss.
Take this over
Thank
lunch.
you.
And I think it is lunchtime, so let's first thank Dima again for a nice talk.
Thank you.